We chose the quadcopter not only because it met our requirements of being an electromechanical system and having at least 20 parts, but we believed that this product would be a great challenge to get us thinking outside the box. Also, the quadcopter is a very popular toy that has a lot of potential for redesign. The quadcopter has been a recent product in the market, really exploding in popularity over the last few years. The product main consumer base is teenagers and hobbyists. There's also been an increased interest in private and military applications to the quadcopter, using it to carry packages and other material over long distances. The background research helped us learn two things. We learned that the rotation of each motor is very important. Two of the propellers spin clockwise while the others spin counterclockwise. This is instrumental in keeping the quadcopter stable in flight. We also learned that the mass-thrust ratio is an important ratio to keep the quadcopter flying properly and stable. The quadcopter's ideal ratio is a 1:2 ratio.
Before we could begin talking about design changes, we had to determine what the potential customer wanted and needed for the quadcopter through customer interviews. Our interview process started with us taking the customer to an open area outside and setting up the quadcopter for them. We gave them a general explanation of the controls, that the left stick controlled the thrust, the right stick controlled the steering and banking, and that pushing left and right on the left stick would spin the quadcopter axially. We only gave these general instructions to test how intuitive it is to fly. Unfortunately, we crashed the quadcopter a lot through interviews and testing. We got it stuck on a roof, stuck in trees, broke a wing and motor off, broke numerous propellers, and one customer hit an unsuspecting girl in the head while she was eating lunch outside. A majority of the questions we asked in the survey were based on a scale of 1 to 5. We asked questions about aesthetics, then we asked about controls and preferences for flight time and location. Also, we wrote down additional and latent customer needs in the margins. From these marginal recordings, we discovered that the customer found it hard to monitor the thrust and steering controls at the same time. What we found is that customers loved the way it looks, they thought it was easy to take off, to fly straight up, and to spin it axially. They thought we could improve the safety and steering controls, and they generally thought it was hard to fly straight ahead, to fly in wind, to land without crashing, and to correct after a crash. Additionally, we found most customers would prefer to fly it both indoors and outdoors, but only found it suitable for outdoor use because of the controls. From these findings, we decided to focus on the functional design change of in-flight stability and the industrial design change of durability, since the drone broke a lot on us.
The disassembly took approximately 15 steps to completely disassemble. The disassembly is relatively simple. All you need is a Phillips #1 screwdriver. The bill of materials is made up of 53 individual parts. The process provided our group with great insights on how the wings and motors are constructed and how the power transmission system works. The exploded view contains all the components that make up the drone. The following figure shows an exploded view of the propeller assembly. The propeller assembly includes the propeller shaft, gears, motor, and motor housing. For the mind map brainstorming procedure, we started with a redesign avenue at the center of the page and branched out ideas organized in different categories. We allowed for extreme ideas without regard for cost or feasibility. The industrial redesign we chose was durability. The categories include changing the material of the quadcopter, adjusting the drone's wing shape, wingspan, landing gear, preventive measures, and changing connections. The functional redesign we chose was stability. The categories include redistribution of mass, vibration reductions, programming atmospheric sensors, propulsion systems, and aerodynamics. Overall, the mind map process gave us many ideas to use for our project. Even ideas that were not feasible were helpful in generating innovative ideas. The 635 activity gave us other ideas, such as using batteries as a pendulum system to increase stability and battery use. This brainstorming process helped us confirm some of our ideas and expand thoughts on redesign for functional and industrial concepts. Functional concept variance includes 1. Increasing the number of propellers, use batteries as pendulum system, make extendable wings, use of compressed air, and changing the aerodynamic of the quadcopter by using the Star Wars TIE Fighter design. The industrial concept variance includes making the main body of a different material, add cages around the propellers, improve landing gear, change wing shape, and add an emergency kill switch.
The purpose of our low-resolution prototype was to demonstrate the feasibility and functionality of our concept variants. As we prototyped them, we realized that they were not practical and very difficult to implement given our time frame. Also, due to the fact that our quadcopter was very small, We were not able to add any features to it, so therefore we need to start from scratch in order to implement elements.
Our team had a lot of trouble trying to perform experiments. This is because the product we chose was a drone where it is difficult to simulate flight conditions, so it was extremely difficult to create an experiment that would give meaningful results. The experimental setup we came up with was having an operator lift the drone up with constant thrust. The drone would then fly while being briefly affected by the wind generated by the fan. It would then cross the finish line. We were planning to use a pendulum concept as our design variable, where we would change the length of the pendulum and the amount of mass attached to it. We believed that a pendulum would create a reaction force to help stabilize the quadcopter in flight. We attempted to perform this experiment, but we found that it was nearly impossible for the operator to keep controlling the drone the same way for each trial. This wouldn't give us good results. It was also difficult to attach the drone in a way that the weight distribution would be equal on all 4 propellers. Due to this, we decided on another experiment. On our final experiment, we kept the fan idea, and instead decided to use 2 of them. One of them would be blowing on the drone from the side and the other fan would blow on the drone from the top. The controller would then lift the drone with constant thrust and then hover the drone for 2 seconds at the height of the side fan. After that, the operator would cut the power off. The design variables we decided on was changing the mass of the drone by adding weights and changing the pitch of the propellers. We believe that changing the mass would affect how the drone is affected by drag force, and the pitch angle would affect the speed of the propellers, thus reducing response time. The response variables we measured were the lift time and the displacement. The lift time is the time it takes for the drone to reach a specified height, and the displacement is how far the drone is from the initial liftoff point. We concluded that it was better to have a propeller with a higher pitch when the mass of the quadcopter was the same. Changing the mass of the drone wasn't beneficial since it increased lag time, and it didn't help much against drag force from the side fan.
Designing our frame was our first step. The key points we had in mind when designing the frame was, the frame must be lightweight and compact, it must be simple to manufacture, while also having the ability to screw various attachments, and finally, have the ability to reduce as much vibration as possible. We thought that using the makerspace, the 3D print would help us save time and run through various iterations of the frame prototypes without putting a dent in our budget. The frame went through 3 different prototypes. All prototypes were designed using SolidWorks. We found fairly inexpensive microcontrollers, which the entire frame design was based on. The purpose of the microcontroller is to stabilize the aircraft during flight. To do this, it takes the signal from the gyroscope and accelerometer on the board and feeds the information into the integrated circuit. This then processes the information according to the software and sends out a control signal to the electronic speed controllers, which then controls the speed of the motor to stabilize the quadcopter. Therefore, we wanted the microcontroller to be able to receive as much accurate information as possible in order for the response to have little error. The first prototype was just a simple square. It was our first time printing in the makerspace, and we wanted to see the results. The second prototype met all our criteria that we had in mind. Most of the vibrations were going to come from the rotation of the motors, so therefore we needed to make the wings as stable as possible. To do that, we made the area around the wings on the frame thicker to keep them in place. The only issue we had was the size was too small, so then the final prototype we made the frame larger. For the wings, we attempted to prototype them in the makerspace, but the quality of the print was poor. The reason was due to the wing length. This caused the 3D printed wing to warp. We needed to think of a different material for constructing the wings. Aluminum was the best choice for us because it was lightweight compared to other metals, easy to machine, durable, and low in cost. We ordered hollow, square aluminum tubes, which were about 24 inches in length and 3 by 4 inches in thickness. Using the mill in the machine shop, we were able to reduce the thickness of the wings, which in return reduced the weight without decreasing the structural integrity. The motors for the quadcopter did not arrive in time for our video, so therefore we had to assemble everything without it.